Okay, let's try to remind ourselves what we did last time and then to continue. So we discussed the linearization of Einstein's field equation. So we started out with a metric of this form. It's Minkowski metric plus h mu nu, and we assumed that the h mu nu were so small that we can linearize everything with respect to these h mu nus and their derivatives. Then we formulated Einstein's field equation now as an equation on Minkowski spacetime for this linearized field. Looked pretty awful, but we saw that we could simplify it by introducing another quantity which is small of the same order as the h mu nu. So we can replace the h mu nus by the gamma mu nus, and then our metric takes this form: eta mu nu plus gamma mu nu minus gamma half eta mu nu. So h is a trace of h mu nu formed with the etas, and gamma is a trace of gamma mu nu formed with the etas. And in this, expressed in terms of these gammas now, the field equation became surprisingly simple. The vacuum field equation was just the wave equation with a standard Minkowski-D'Alembert operator, provided we use the so-called Hilbert gauge, which is possible by a coordinate transformation. So then the equations become pretty simple. Okay, we need this as a constraint, as a side condition, and apart from this we can just work with the wave equation. So that's the source-free Einstein equation in the linearized form expressed in terms of the gammas. There's still a freedom to make coordinate transformations. We can still go from x mu's to x mu tildes by, well, just making a translation of the origin. That's something trivial. And we could make a Lorentz transformation, and we could make an arbitrary transformation, which is with a function which depends on the axis in an arbitrary way, but which must be smaller first order, so that this linearization assumption is still satisfied. And if we have the Hilbert gauge condition imposed, then these functions are no longer completely free. So that's what I called C, the transformation formula. And if we want to preserve the Hilbert gauge condition, then we have to require that the f mu's satisfy the wave equation. So there's still a freedom to make coordinate transformations, but it is restricted to these f's. Okay, so this was the general framework. And then we discussed plane harmonic wave solutions of this expression. So we made an ansatz for the gamma mu nu, that it is a plane harmonic wave. So this depends on x. And it has a constant amplitude, and the x only enters into the phase. So that's what we call a plane harmonic wave. These are real. That's a real wave covector, and it's a complex amplitude. It's just a convenient way of writing a real function. And if we feed this into the wave equation and into the Hilbert gauge condition, we get conditions on the k and on the amplitude. This was the last thing we calculated last time. So the field equation. So if we feed this ansatz into this equation, then we get the condition that this covector must be light-like. So we got the condition that this must be 0, which means in physical terms that plane harmonic waves in the framework of this setting travel at the speed of light on Minkowski space. Yeah, with the speed, they are light-like with respect to the Minkowski metric. Indices are raised and lowered with eta. And the Hilbert gauge, this here also gives a condition. This gives the condition that k mu, a mu nu must be 0. So this is a condition on k only. It doesn't restrict the amplitudes. This does restrict the amplitudes if the k is given. So if I prescribe the direction in which my wave should travel, then this restricts the possible amplitudes. So that's what you would call a restriction of the polarization state, right? Any restriction on the amplitude for a given k, that's what we call a polarization. Yeah? And the question is now, is this the only polarization condition we get? And the answer is no. Actually, That's the reason why I have written this again. We still have the freedom to make coordinate transformations, and we can use them in order to impose additional conditions on the H mu. So this was the first condition on the H mu. Let's call this H for Hilbert gauge. And my claim is there are additional conditions, and that's what we want to derive now. So my claim is it is possible no, let me begin in a different way. Let u mu be given with eta mu nu u mu u nu is minus c squared. Is this better now? So this is a constant 4-velocity vector on Minkowski space. So this would fix an inertial system, right? The motion of the observers in an inertial system. And if I have something, then I claim that I can impose additional conditions on the A mu nu's which involves this u. So then it is possible to make a coordinate transformation of this form here with this condition, so that the Hilbert gauge condition is preserved, with box f mu is 0, such that two additional conditions hold. The first condition is that u mu A mu nu is 0. That's what one calls a transversality condition. So let me write T1, T-like transversality. So if you look at this condition and combine it with this condition, then it says the following. This means that the A mu nu is symmetric. Yeah? So if you contract over the first index or over the second index, doesn't matter. So this means that the amplitudes are purely spatial with respect to this 4-velocity u mu. Yeah? So in an inertial system where this is the 4-velocity of the observers, the A mu nu is purely spatial, so it has only spatial components. If you combine it with this here, that it is perpendicular to the propagation vector of the wave, then it says that the propagation direction of the wave and the amplitudes are perpendicular. So this would mean that the amplitudes are transverse. Yeah, they are perpendicular to the direction in which the wave travels. So this T stands for transverse. And the second condition is that this here is 0. So you could also write it in this way. Yeah? We raise and lower indices with the eta. And that's what we would call the trace-free condition. Yeah, that the A mu is trace-free. So that's T2. So the second T stands for trace-free. And because of the two T's, one calls this transverse traceless gauge. Oops. Or the TT gauge for short. So the claim is that if I am in the Hilbert gauge, I have already made my decision I want to work in the Hilbert gauge, then there's still a freedom to make coordinate transformation, and I can use them in order to impose two additional conditions. That's what we call the transversality and the traceless condition. So the TT gauge is a subclass of the fields in Hilbert gauge. Yeah? The Hilbert gauge was already established before, and then we specify even more the coordinates by the TT gauge. Okay, the proof is rather simple but boring. I will not do it here in full detail on the board. I will type it out, and I will just tell you the essential steps here in the lecture. You make actually two coordinate transformations, one after the other. So the first coordinate transformation will be done, will be a pure Lorentz transformation. So I have only this term here. Yeah? So the little A mu is 0 and the little F mu is 0. And I can use this. Well, we remember what the Lorentz transformation does. The Lorentz transformation maps time-like directions onto time-like directions. And we can choose the transformation in such a way that this given u mu now becomes the 4 direction, the x naught direction. Yeah? So that in the result, as a result of this transformation, the u mu is just c times delta mu 0. So it has only a 0 component. So geometrically, this means we make a Lorentz transformation which maps my u mu onto the vertical direction, yeah, the t direction. So that's the first trafo. That's rather trivial. And the second, that's a non-trivial one. That's one with an f mu. So now we go from x mu to x mu plus f mu from x. And we choose, I think that's not enough space. So f mu of x is the following. It's a real part of something which has the same phase as my solution. Yeah, I start out with a solution. This is shorthand, what I've written here. So what I meant is, let's assume we have a solution. We have something of this sort. Then the claim is I can make such a transformation that this additional conditions hold. So I start out with a solution. I have something of this sort. So I have an a mu nu and I have a k rho. Yeah? And with this k, I form now this expression here with an amplitude, c mu. And of course, I have to tell you what the c mu is. Well, actually, I think I've written the c with the lower indices. So we raise and lower indices with eta. That's now, if I give you one, you can easily write the other. So the c naught is minus a mu mu k naught minus 2 eta ij ki kj ao, no, not kj, sorry, aoj, that's it, and divided by 4 k naught squared. And the cj, the spatial components, the cj's are minus 1 over k naught aoj plus kj c0. So if you perform such a coordinate transformation, then you can check. Well, first of all, that the Hilbert condition is preserved. That's obvious. Yeah, we know already that all expressions of this sort, where this is a light-like vector, satisfy this condition. So this wave equation is satisfied. So the new coordinate system satisfies again the Hilbert gauge condition. And then you have to check these two conditions. So you write them out with u mu is just a multiple of delta 0 mu. And you have to calculate a while. So it's not just 1 or 2 lines, it's a little bit more. But it's trivial algebra. So I think I will not do this here on the board. So I will type it out. And if you don't believe it, you can then follow it step by step. So if we believe this, if we believe that this is true, that this can actually be done, then we see that we have additional conditions on the a mu nus. So we have less degrees of freedom. We have stronger restrictions on the polarization as it seems at first sight. So we can now do the following. So we can, first of all, I should emphasize that this traceless condition implies that now the little gamma vanishes, right? If you form the trace of this, so let me write this down, that's important. So in the TT gauge, we have gamma equals 0. Why is that? Well, gamma was just eta rho sigma real part of a rho sigma e to the I k, say tau, x tau. And you see, if we have this condition T2, then this is 0. Yeah? This can be taken under the real part because it is real. And then eta rho sigma, a rho sigma is 0. That's just the condition T2, right? So the gamma is 0. This means that in the TT gauge, our metric, G mu nu, is just eta mu nu plus gamma mu nu. Yeah? Now the gammas are the perturbations of the etas, which is not true in general. In general, I have this additional term here. But in the TT gauge, I don't have this term. Okay, now let's count how many components the amplitudes have. So in coordinates, it's the easiest way to calculate components if we do it in a particular coordinate system. So we can choose our coordinates, for instance, in such a way, as we have done it already here in the proof, that u mu is just our vertical vector. And now the k mu is a light-like vector. And I can make a spatial rotation. Yeah, I can make a transformation with the lambda, which is purely spatial. Spatial rotations are particular Lorentz transformations, right? So I can use this in order to make the direction in which the wave travels the 3 direction. So I have zeros in the middle, and I have here and here something, and it must be the same number because this is a wave is a light-like vector. And in order to link up with standard notation, I denote this by omega over c. Then the omega is the frequency. Okay, and coordinates with, I forgot this word here. I have now my condition. So the first was the Hilbert condition. The Hilbert condition was that 0 is nonsense. Where was it? Here, this condition. K mu, A mu nu. Well, and in these coordinates, where the k is either 0 or it's omega over c, right? And when is it omega over c? It's omega over c if the mu is 0 or 3. So I get a 0 nu plus a 3 nu. Okay, so that's the condition which comes from the Hilbert gauge. Then I have the transversality condition. This was 0 is u mu, a mu nu. And u mu is just c times delta mu 0. So this is this here. Okay. And the traceless condition, T2 was 0 is eta mu nu, a mu nu. So this begins with -1 if both indices are 0. So I get minus a naught naught. And it's +1 for the cases where they are spatial and equal. So I have plus a11 plus a22 plus a33. And now let's count how many components we get. So this condition tells us that my amplitudes vanish whenever one of the indices is 0. Yeah, so this is symmetric. So it doesn't matter which index is 0. Then we use this equation, which tells us, we know now that this is 0 anyway, so it tells us that also if one of the indices is 3, we must get 0. So the only cases where I get something different from 0 is when both indices are either 1 or 2. Yeah? These are the only ones. And how many have I? I have a11, a22, a12, which is the same as a21. And then this condition tells me that a11 and a22 are dependent on each other. So this is 0, this is 0. So a11 is minus a22. So I'll end up with only 2 independent components. So independent components of a mu nu are what? So the first one is a11, which is the same as minus a22 by the condition T2, right? And the other one is a12, which is of course the same as a21. Here the a's are symmetric because the gammas are symmetric. The gammas are perturbations of the metric, and the metric is symmetric. So these are the 2 degrees of freedom which our amplitude has. And for reasons which will become clear in 5 minutes or so, one denotes this as a plus and this as a cross. So if this is non-zero, then one speaks of a plus mode, and if this is non-zero, one speaks of a cross mode. I will explain these words in a minute. So they are analogous to right-handed and left-handed polarization in the electrodynamic case. Yeah? So you have also 2 basic states. You can write everything as a linear combination of them. And for the electromagnetic waves, these are right-handed and left-handed. Or you could use linear polarization in this plane and linear polarization in this plane. That's another alternative. Here we have two polarization states, the geometric meaning of which is not so clear obvious. We will discuss them in a minute. So I should also remind you that these are complex numbers. So if you want to write it as a modulus times a phase, then you could write it in this way, right? It's a modulus a plus, which is a positive real number, times a phase, and analogously for this here, ax absolute And it's a different phase, of course, in general. So let's say psi. Okay, so we will have to discuss this, and we'll try to understand what these basic polarization states do. So what actually a gravitational wave does, in which way I can observe it. So that's not so obvious. In particular, after this problem we have done on the last worksheet. Yeah, those of you who have been at the tutorial yesterday where we discussed these metric which looked like a gravitational wave, but then it turned out it was no gravitational wave. It was just Minkowski spacetime written in funny coordinates. So it's not so obvious just by looking at the expressions for the metric coefficients to guess what the metric actually describes. And the way, the method by which you can really understand what a gravitational wave does is the following, that you consider freely falling particles. And you see what the wave does with these freely falling particles. Then you get a good geometric understanding. So one possibility is, and we will do this now, one possibility is we arrange particles, freely falling particles, on a sphere. And then we let them go. Yeah, we let them freely move. And now the gravitational wave sweeps over them. So they will rearrange them. They will change the distances between these freely falling particles. And what they do to this cloud of particles, in which way they modify them geometrically, this will give us a clear idea what the gravitational wave is about. And we will see that here we have a motion, with respect to a vertical crosshair, and here we have a motion with respect to a crosshair which is under 45 degrees. That's the reason why one is called the plus mode and one is called the cross mode. So in order to do this, we have to discuss freely falling particles in the space-time. Yeah? It doesn't tell you anything if you just discuss how coordinate distance changes. That was what we wanted to learn from the exercise yesterday, right? Yesterday we had a metric where we saw that the coordinate distances oscillated periodically. But this was just a matter of the coordinates. I had introduced funny coordinates. Yeah, it doesn't tell me anything about the real geometry of the space-time. So we have to look, for instance, at freely falling particles. That's something which is independent of coordinates. And my claim is that in the TT gauge, world lines x mu of tau with x mu dot of tau is this u mu. Yeah, the TT gauge refers to a particular four-velocity vector, u mu. And my claim is that if I now consider the integral curves of this particular four-velocity field, so in this coordinate system we have chosen down there, this will just be the t lines. Yeah? And my claim is that they are geodesics. And on the basis of this observation, which I will prove in a minute, on the basis of this observation, we can then understand what the plus mode and the cross mode do to freely falling particles. So, well, we want to deal with the geodesic equation, so we have to calculate the gammas, right? For the geodesics, we need the gammas. So I calculate the gammas mu sigma in the TT gauge. Hopefully everybody remembers how the gammas could be calculated from the metric. We have these three terms with partial derivatives of the metric. The summation index is rho, 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 and the speaking indices are nu and sigma, nu and sigma, nu and sigma. So now we have this form. Where is it? Here. This form of the metric here. Eta mu nu plus gamma mu nu. And well, the eta mu nu's are constant. So if I begin with a bracket here, then only the gammas appear here. Yeah? So I have here only the gammas. Oops, minus gamma nu sigma. And they are first order already. So only the zeroth order term for the prefactor will be of relevance. So this begins with eta mu rho. And then come terms which involve gammas, but they give quadratic terms. So according to our general setup, we ignore them. Well, and now I insert my TT wave. Yeah, gamma is a TT wave, a wave in TT gauge. So what is this? So where's the metric? Oops. Here it is. Here it is. So I differentiate this. I have to differentiate this in order to calculate these three terms. So I get a real part. Oops. I get a real part. The amplitude is given by this indices. So this is A rho sigma. And I differentiate with respect to x nu. So I get an I k nu. From the second term, I get nonsense. An amplitude with indices rho nu. And differentiation with respect to x sigma gives I k sigma. And here minus A nu sigma I k rho. And then the phase factor, e to the I k tau x tau. Okay? So that's my expression for gamma. And now I calculate the left-hand side of the geodesic equation, and hopefully I get 0. So now I calculate x mu double dot plus gamma u nu sigma x nu dot x sigma dot. Yeah? If this is 0, then this means that x mu of tau is a geodesic. And x mu with 1 dot was a u mu. So this is u mu dot. But this is 0 because u mu is constant. Yeah? And this here is u nu dot. And this is u sigma dot. And on the right-hand side, I have this expression multiplied now with u nu, nonsense, no dots, of course, no dots, multiplied with u nu and u sigma. So I just copy what we have there. So I have 1/2 eta, how did I call the indices? I can't read this. This was a mu, right? Gamma mu nu sigma, yes, fine, mu rho. Mu rho, then the real part. And now I have to multiply each term with u nu u sigma. So I get A rho sigma I k nu u nu u sigma, then plus A rho nu I k sigma u nu u sigma minus A nu sigma I k rho u nu u sigma and the phase factor. And now we remember that we are on the TT gauge. And the TT gauge, A rho sigma times u nu is 0. Yeah? This was a transversality condition. Sorry, u sigma, of course. There must be a summation over one of the indices. And here, A rho nu times u nu, this is 0. And here, A nu sigma times u nu is 0. So the whole thing is indeed 0. We have geodesics. Yeah? So this might come as a surprise, actually. What does this mean? What have we calculated now? So if we do in coordinates with u mu is c delta mu 0. So this means u mu is just a vertical vector. We have the following. If I have here ct, which is ignored, and here I have my spatial axis xi. Now I consider one ignored line. So that's a geodesic according to this calculation, right? And if I choose any other ignored line with spatial coordinates xi, say, then this is again a geodesic. So they are both freely falling. So if you look at the picture, you might say, well, there's no gravitational waves, there's nothing happening. Right? They are just sitting there at their fixed coordinates, and they fall freely along these vertical world lines, and there's no motion, no relative motion. But this is a wrong conclusion. The relevant thing is, what is the distance doing? If I really measure the distance with a metric. Yeah, what the coordinate values are doing, if they are constants or not constants, is completely irrelevant. That's a matter of the choice of coordinates. The relevant thing is, what is the distance doing? If I really measure the distance of these 2 points, yeah, that's a point, a mass point falling in free motion along a t-line, and that's another freely falling particle. what is the distance measured with a metric doing? Does this change in the course of time? And that's what indicates a wave. And actually it does change. We will calculate it now. Yeah? So that's the important thing to distinguish. Coordinate differences are irrelevant. The coordinate difference between these two word lines is constant. Yeah, just the xi's. But this doesn't tell you anything about the real geometry. The relevant question is, what does the distance do? Really the measured distance, measured with a metric. And in order to calculate this, well, I would have to calculate, well, this is purely spatial, right? So the distance here in these horizontal spaces, only the spatial coordinates of these word line matter. And x naught is just a coordinate which parameterizes the points on the word line. So the distance is really a distance with respect to a spatial metric. So I have only spatial indices here. And this goes along the line where all three spatial coordinates are 0. Yeah, this is this word line here. X naught moves upwards, and the other three coordinates are 0. And then I measure the length of the connecting vector, which starts here and connects to the neighboring word line. So I measure the length of this thing here, xi, xj. And then we see what this does. So this is the length squared. Yeah, the distance, the measured physical distance squared for these two mass points. So I have two mass points in free motion, and I measure the distance with a metric, and I see how this changes in the course of time. That's what I'm calculating now. And we can calculate this. We just have to insert our expressions for the metric. So this begins with an eta ij, xi, xij, and then comes a gamma term. And gamma, of course, I have to evaluate at this point here, x naught, 0, 0, 0, xi, xij. Okay, that's eta. Well, these are spatial indices, so the spatial components of the eta are just the Kroneckers, right? So eta ij is the same as delta ij. So this is just the standard Euclidean length squared of this connecting vector. Yeah? So if there were no gravitational wave, then this would be the distance, and it would be constant, of course. But there is a gravitational wave, and that's the second term. Now let's calculate what this gives. So this is the real part of aij, xi, xij, e to the I, and now comes k tau x tau, at this point evaluated, so only the 0 components are present. Yeah? Because x1, x2, and x3 are 0. I'm starting at the origin here. I'm considering the connecting vector from the origin to a neighboring point. And now we can evaluate this in terms of our two independent components, A plus and A cross. So we see this gives something if the indices I and j are either both 1, both 2, or one is 1 and the other is 2. These are the cases which give something. Yeah? So let's begin when both are 1. Then I have A11 and A11 is A plus. And this comes with xi1 squared. Yeah? This is A11 xi1 xi1. And then A22 xi2 xi2. A22 is our minus A plus, so I get minus xi squared. Okay? And this phase factor, well, x naught is c times t. K naught with the upper index was omega over c. With the lower index, it's minus omega over c. So this is minus I omega t. So these are the terms with 1, 1, and 2, 2. And then comes the term with where one index is 1 and the other is 2. Where this is 1 and this is 2, and the other one where this is 2 and this is 1. So I get twice the cross mode with xi1, xi2, and again e to the minus I omega t. Okay? So these are the terms where both indices are equal, either 1 or 2, and these are the terms where they are unequal, where one is 1 and the other is 2. And where we have A plus and A cross already written in terms of modulus and phase. So we can easily form the real part. So this is real, yeah? Psi plus, not equal. So that's psi1 squared minus psi2 squared. And then the real part of a plus times e to the minus I omega t. And this is the modulus of a plus times cosine. What is the phase of a plus? Phi. Phi minus omega t. Yeah? If I insert for a plus modulus times e to the I phi, then I have just to form the real part of e to the I phi minus omega t, and that of course gives the cosine. So that's this term here. And the other term, so I have 2 times psi1, psi2 is real. And then I have the real part of a cross times e to the minus I omega t. That's a cross modulus, and the phase was psi minus this omega t. So that's the measured distance. Yeah, the measured distance between these 2 points squared. And we see this oscillates. This oscillates. For the plus modes, it oscillates with this amplitude. And for the cross mode, it oscillates with this amplitude. And it's harmonic with frequency omega. So now let's try to produce plots, which is a little bit difficult to do it on the board with a free hand, but let me try. And then we understand what a gravitational wave does to particles which are put into the way of the gravitational wave. So this formula which we have derived there holds for any connecting vector psi. So I start at the origin and consider a connecting vector to an arbitrary neighboring point. And now I consider the case that delta ij, psi j is constant. So I consider particles which are arranged on a sphere. And I see how they oscillate when the gravitational wave influences them. And that's what I will try to draw. So the relevant things happen, of course, in the plane transverse to the propagation direction. Yeah, the wave propagates in the 3 direction, and the amplitude has only 1 and 2 components. So it propagates in the 3 direction, and the amplitudes are only in the plane perpendicular to the propagation direction. So what I plot is, of course, the psi1, psi2 direction, right? So I plot the plane perpendicular to the propagation direction. That's the propagation direction of the wave. And let me begin with the plus mode. So the plus mode, this means that a plus is different from 0 and a cross is equal to 0. So I arrange particles on a sphere. Okay, I'm not Albrecht Dürer. Albrecht Dürer was able to do this with perfect accuracy. And then he could put a dot right at the center of the circle. But well, by my standards, that's not too bad. And now let's see what the wave does. So I have only the first term. Yeah, I'm only talking about the plus mode. So you see where the extremal values are reached when omega t is phi or phi plus pi. So let's begin with omega t is equal phi. Then the cosine is plus 1, right? If the cosine is plus 1, I see I have in the psi direction a positive displacement. Yeah? That would be a circle. If I had only this term, then it would be a circle. And now I see this term gives me a positive displacement in the one axis, and this gives me a negative displacement in the 2 direction. So here I have positive, and here I have negative. So if I connect this, I get an ellipse. Yeah? So the gravitational wave distorts my sphere into an ellipsoid in the direction transverse to the propagation direction. And half a phase later, so this would be at omega t equals phi plus pi. Then the cosine is -1. Then I have just the opposite situation. So then I have a negative displacement in the x1 direction and a positive displacement in the x2 direction. And I have something like that. And this goes rhythmically back and forth, right? If I have phi plus 2 pi, then I have this again. If I have phi plus 3 pi, I have this again, and so on. Yeah? So there's an oscillation, that's the propagation direction, there's an oscillation in this way. So this comes together, and this is stretched, and then it's the other way around. Then this is stretched, and this moves apart from each other. So that's what the plus mode does to particles which are arranged on a circle. And now you understand why it's called a plus mode, right? The axis has the shape of a plus in this case. So now let's consider the cross mode. The cross mode is the one with a plus equals 0 and a cross different from 0. Psi1, Psi2. So again, I have my particles in the mean on a circle, and in this case I have another phase shift psi. And we see, well, here I have the maximal and the minimal elongation in the directions where the product of psi1 and psi2 is extremal. And that's just in the directions under 45 degrees. Yeah? So you can transform these two terms into each other just by rotating your axis by 45 degrees. Then one goes into the other. So in this case, I have here my maximal elongation, and here's a minimal. So I have an ellipse of this sort. Oops. Oh yeah, okay, it's supposed to be an ellipse. And if I do it half a phase later, psi1, psi2, here's my circle. Then I have here the minimal elongation, and here the maximal elongation. It looks this way. So this would be for omega t is psi plus 2 pi. And that's something which is, of course, measurable. Yeah? That's something which is measurable. So if I put particles into the way of the gravitational wave, I could see how their distance changes just by measuring their distance. And if I see such a change, then I know, aha, that was a gravitational wave. And that's precisely the way in which people try to detect gravitational waves. So there are two methods, so two types of gravitational wave detectors. The first are the so-called bar detectors. They are just cylinders, typical aluminium or something like that, maybe that shape, 1 or 2 meters long. And the idea is that if a gravitational wave sweeps over this object, then it produces oscillations in the direction transverse to the propagation direction of the wave. Yeah? So if the wave comes from there and goes in this direction, then it would produce an oscillation in this direction. Yeah? And well, one expects what sort of frequency a gravitational wave could have if it comes from a certain source. And so one knows what shapes the cylinder should have in order to get a resonance frequency. And that's what people tried since the 1960s. So these are in use since quite a while. It's 1960s, and the person who invented them and worked with them for many, many years was Joe Weber. He died a while ago. But these bar detectors are still in use. They have shifted a little bit to the back by the other type, but they still do exist, and some of them are still in operation, and one still tries to find gravitational waves with these bar detectors. Until now, none has been found, of course. Yeah, so I would have said this already. So the second type, that's a more modern and more this is the type with which more optimism is connected. These are the so-called interferometric detectors. Here the idea is to use Michelson interferometers, and the distance which is changed by the gravitational wave is the distance between the mirrors. Yeah, so the path the light is traveling, and this of course gives a shift in the interference pattern. So the idea is that the mirrors begin to change their distance if a gravitational wave moves over them. So of course the mirrors must be in free motion. So they are on a string, so they are free to swing in this direction. And actually, the production of this string, this was one of the most delicate problems in the construction of these interferometers. So to make sure that the motion is not inhibited, the motion in this direction, right? Of course, the motion upwards and downwards, this is inhibited. Of course, they have to do it in the gravitational field of the Earth. So we can only detect this horizontal motion, of course. And yeah, these interferometers, they are in use now since 10 years roughly. There are quite a number of them. There's here GEO 600. That's near Hanover. And this has an arm length of 600 meters, an effective arm length of 600 meters. That's why it's called GEO 600. Then there are the 3 LIGO detectors in the United States. So this is USA. These are actually 3 detectors at two sites. They are bigger. So they have an effective arm length of, I don't know, I think one is 2 kilometers and the other 3 kilometers or something in this order of magnitude. And they are also in operation since almost 10 years now. So by the way, the two teams are very closely collaborating. It is one team. Yeah? So they have really joined forces and they exchange their data. And it's not the case that they don't find anything, so that they just look at the screen and there's nothing. Everything is just a null line. No, that's not the case. They see a lot of signals. The problem is to find out which signals really come from gravitational waves, because there are so many other influences. So GEO 600, of course, could easily measure the tides of the North Sea. The tides of the North Sea have a strong effect on GEO 600. Although Hanover is not directly on the coast of the North Sea, right? It's fairly far away, but they are sensitive enough in order to find this. And the slightest sort of earthquake, of course, will be detected by these interferometers. So the problem is to filter out the correct signals. And what they do actually is that some teams produce mock data. So they feed into the system mock data, and they try to find out if the other people who do not know what mock data are fed into it, if they can really detect it, or if they are led onto a wrong path by this. So to filter out the true signals, that's the main problem. The main problem is not just to measure anything. They do measure a lot of things. And there are other detectors. So there's a Japanese one, which is in build now, which is supposed to be very sophisticated and which might open new routes. And one of the LIGO detectors is supposed to be moved to India, so that one have also one on the Indian subcontinent. In Australia, there's something going on. And then they are planning to send a space-bound interferometer. So this is in the planning stage. So this would have an effective arm length 5 million kilometers. So it would be able to detect gravitational waves in quite a different frequency range than the other ones. But well, you know about these finance problems of the space projects. So when LISA actually will fly is an open question. So I think the present plan is something like 2018 or so, but I wouldn't bet on it that it really is launched by this date. So this is something for the future. But these things they operate since quite a while. And yeah, as I said, until now there was no observation. There was no signal where the people could really be sure that it came from a gravitational wave. So that's something we are urgently waiting for, that actually a gravitational wave would be detected directly in this way. I've already talked about this indirect proof, in quotation mark, of the existence of gravitational waves by the binary pulsar, for which Taylor and Hulse got the Nobel Prize in the early 1990s. So one just observes that a binary system loses energy, and the interpretation is that this energy is radiated away in terms of gravitational waves. But the gravitational waves have not been detected directly. Yeah? So there was never an event where a detector really clicked and you said, aha, now a gravitational wave had come into it. So that's what we are waiting for. Okay, and that's the theoretical background so that you understand what these people who are working with these detectors, what they actually expect to see. So that's what a gravitational wave should do with particles which are brought into its way. Okay, so that's what I wanted to say about the plane harmonic waves. And then there's another important subject open, and I will speak in the rest of this lecture, and maybe tomorrow for half an hour or so on this. This is a relation to the source. Here we haven't talked about the source at all. Yeah, we were away from the source. We were dealing with a vacuum field equation. So the idea is very far away from where we are. There's a source, there's some rapid motion of gravitating objects. They produce a gravitational wave, and now the gravitational wave arrives at our place here. And when it arrives here, it is so far away from the source that the wavefront is more or less plane, and that it's, to a good approximation, maybe even harmonic. And then we can use this approximation. And this tells us how the wave looks here at our position. But it doesn't tell us anything about the source. For that, of course, we have to deal with the field equation with the source, with the T mu nu. And we have to see what sort of T mu nu actually would produce a gravitational wave. So that's what I would like to do now. So to tell you the gist of the story already at the beginning. So the main result will be that what we need is a time-dependent quadrupole moment of the source. So in electrodynamics, I hope everybody remembers that in the far field, the dominating term is a dipole term. Yeah, if you want to produce an electromagnetic wave, what do? You produce a Hertzian dipole, right? So one way is just take a charge and move it up and down rhythmically. That produces a nice dipole radiation, which can be observed in the far field. For gravitational waves, this doesn't work. There's no dipole radiation. The leading order term is a quadrupole term. And that's what we want to derive now. We know already that a monopole would not do. By the way, this is also the same in electrodynamics, right? If you have a spherically symmetric charge and it's just pulsating, then you have the Coulomb field outside. You have no time-dependent field, no wave. And that's the same for gravity, according to general relativity. That's the Birkhoff theorem, right? If we have spherical symmetry, even if the star is pulsating, as long as it is spherically symmetric in the outside, we just have the static Schwarzschild metric. So there's no monopole radiation, neither for gravitational waves nor for electrodynamic waves. And then the next order term would be the dipole term. And this gives something for electromagnetism, but not for gravity. For gravity, we need the quadrupole term. Quadrupole is the leading order. So I guess that's section 7.3. Let's call it relating gravitational waves to the source. So now we have to deal, of course, with a field equation with source. So this was box gamma mu nu is 2 kappa T mu nu. And we still use the Hilbert gauge. So we have this condition. And the idea is that we have a T mu nu, which is non-zero in a certain region of space. So we could say it is non-zero inside a ball of a certain radius. And outside this ball, we should have vacuum. So outside of this ball, could use the equation with a zero here. But now we want to look also at the part where the T mu nu is non-zero. And then we have to solve this with a non-zero right-hand side. So we have to solve an inhomogeneous wave equation. So I hope everybody remembers how the general solution to this inhomogeneous wave equation for a given T mu nu. Yeah, let's assume somebody tells us what the energy momentum tensor is. So we know this here. So this is our unknown. We want to solve this wave equation. So we were interested in the general solution to the inhomogeneous wave equation. And I hope everybody remembers what this is. This is a general solution to the homogeneous wave equation with a zero plus one particular integral of the inhomogeneous equation. So the only task we have to fulfill is we have to find one particular integral of the inhomogeneous equation. And well, that's what one learns in electrodynamics. Well, one learns it for a quantity with one index, but that's completely irrelevant. Yeah, every component satisfies exactly the same equation here for this quantity with two indices than for one indices. And well, there's one particular integral which is constantly used in electrodynamics. That's what we call the retarded potential, right? We have a given source with one index, and we want to solve this equation. We want to find one particular integral for this equation. Then it's given by the famous retarded potential. And we can just carry this over into gravity. So that's what we want to write down now. So let me begin with what I've said already. So the general solution to the inhomogeneous wave equation is the same as the general solution to the homogeneous wave equation with a zero here on the right-hand side. Homogeneous wave equation, where we know what the general solution to the homogeneous wave equation is. That's a superposition, an arbitrary superposition of plane harmonic waves of the sort we have just studied them in the preceding section, right? Yeah, in the preceding section we have studied plane harmonic wave-like solution of the homogeneous wave equation. And any superposition of this, because of the linearity, is again a solution. So when we assume that our field is nice enough so that we can do a Fourier decomposition of it, then we get the general solution just as a superposition of plane harmonic waves. And then we have to add plus one particular solution to the inhomogeneous equation. And so a particular solution, such a particular solution, is known from electrodynamics. And it is what one calls the retarded potentials. So retarded potentials are constructed in the following way. So here in this case I want to have it for a quantity which is called gamma mu nu. Well, there's a funny factor which I never know by heart. One over 4 pi. And then I have an integral over space. Not over space-time, just over space. And then I have the right-hand side, my source, which in this case is 2 kappa T mu nu. T mu nu, but wait a minute. If I want to have my field at coordinate x, which have, which are ct, x, that's not enough space, sorry for this, x1, x2, x3. Or let me introduce a shorthand notation. I think that's a good idea. Let me write it in this way. So I have r is x1, x2, x3. And I will also write r without an arrow for this here. So this is root x1 squared plus x2 squared plus x3 squared. So then I can write here for the argument just ct and r. And I have to take my, my source, this here, not at the same time t, but at the retarded time t. That's why it's called the retarded potential. So I write here t, as an argument, let me just write t here. Yeah? So this depends on the 4 x's, and the 4 x's are determined by the time t and the 3 vector r. So this is t minus r prime over c. You will see in a minute what r prime is. And here the argument is r prime divided by the distance, r minus r prime and dv prime. So the integration is over a volume, and the integration variable is the r prime. So dv prime is dx1 prime, dx2 prime, dx3 prime. So you integrate over all of space. Well, your T mu nu is non-zero only in a finite region, in a bounded region. But I have to include, I forgot the 4 pi. I have to include all the sources. So I have to integrate over all of R3. Then I take my source at the retarded time. So that's the time which a light signal needs in order to travel from the vector r, at which I want to know my field, to the position r prime, where my sources sit. Yeah? And that's what I have to calculate. So you can easily check that this satisfies this equation. Yeah? So this, of course, involves a differentiation with respect to the unprimed coordinates. Yeah? So you can pull it under the integral, and you have to differentiate with respect to these arguments, the unprimed arguments, not the primed ones. And well, if you do the calculation correctly, then you will find very quickly that this is in fact satisfied. So I should draw a picture for this. So we have here my origin, and my vector r prime moves over the region where the energy momentum tensor is different from 0. So here I have T mu nu non-zero. So this, let's say that's a sphere of radius r. Inside the sphere of radius r, so this here is the radius r. So T mu nu is different from 0. And outside of it, it is equal to 0. Here I have T mu nu equal to 0. And here I want to know the field. I want to know the field here at this point. So that's the vector r. And I want to know it at a time t. Yeah, I want to know the field at the time t at the position r. And that's a formula which tells me what I have to do. I have to consider the sources here at all positions r prime inside this sphere at the retarded times. So I have to take into account that a signal from the source to the observer moves at the speed c. Yeah? So if you juggle your sources here, this will not arrive here immediately. It will arrive with a certain retardation, yeah? Because it can only travel with a speed c. This equation, this operator, describes propagation at the speed c. Yeah? So it's also valid for gravitational waves. Gravitational waves in this approximation formalism move at speed c on Minkowski space. So that's the reason why the same retardation factor occurs here. So that's one particular solution. And where the general solution is found by adding a solution to the homogeneous wave equation. This would be something related to waves coming in from infinity, right? Of course, that's not the only solution. That's a solution which comes, yeah, so to speak, from the sources directly. But there could also be a wave coming in from infinity, which is also present on my space-time. And this would enter into these terms here. So if my sources are the only sources of gravitational waves, if no gravitational waves come in from infinity, then this would be the complete solution. Yeah? But in general, I would have to add something coming in. And now we want to find out, what sort of source, so what sort of T mu nu would produce a nice gamma mu nu, so that I really observe something at a large distance, that I observe something in the far field. Yeah? So I'm not asking about detecting gravitational waves here in this area. So you might think of a binary, a binary star. So for instance, this binary pulsar, which was investigated by Taylor and Hulse. So you have two stars circling around each other. So they produce here an energy momentum tensor, a time-dependent energy momentum tensor. And I want to detect the gravitational waves produced by this object. I do not do this here in this area. I'm not at the position of the binary. I'm very far away on Earth. I do it there at a large distance. So the question is, if such a wave is produced, what does it produce at a large distance from the source in the far field? That's what we want to discuss. And we will find that the second derivative of the quadrupole moment is a relevant quantity which arrives at large distances. So that's our goal now. Okay, so that's what we want to calculate now. To that end, we will make the far field approximation. So we will add to the approximations which are already in the game. Yeah, we have already done approximations. We have linearized the field equation. But now we will make a further approximation. We will assume that we are far away from the region where the wave is produced. So we will assume that the r is much bigger than the r prime. Yeah? And for this, I have to write this expression here explicitly. So let me calculate this distance, r minus r prime. I want to evaluate this and then approximate it in a certain way. Of course, this can be written as the square root of r minus r prime dot r minus r prime, right? By the way, the calculation I'm now doing, you have most certainly seen in your electrodynamics course, for the electrodynamic situation. When you derive the Larmor formula, for instance, you do precisely the same thing. The only difference is that these things have only one index. Yeah? Here you have the electromagnetic potential with one index, and here you have the current density, J. Otherwise, and of course not this kappa here, but another constant. Yeah? But apart from this, it's exactly the same thing. And then you make this expansion. So this is the square root of r squared minus 2r prime plus r prime squared. Yeah? So as I said, I will just use this shorthand notation here. So for r absolute, I write r without an arrow. So I have r squared. Then I have 2r, r prime, and then the angle between these two things. Let me write theta for this. Cosine theta. Yeah, that's the angle between this angle here. This angle. And the last term is r prime squared. And I want to make an approximation that r prime is smaller than r. So I would take the r out of the root. So I write r in front of everything. Then I have 1 minus 2 r prime over r cosine theta, r squared divided by r squared. And for this I can make a Taylor expansion. So I can write this as r minus, well, from expanding the square root I get a factor 1/2, right? 1/2 times 2 times r prime over r cosine theta. And then I get the terms which are second order here. Well, actually, if I say I consider the far field, then I do even something more. I go even one step further with the approximation. I just consider the zeros order term for the square root. So this would be this expansion. And I insert this into my expression for gamma mu nu. So I get gamma mu nu at time t, and position r is what? So I insert for the r minus r prime in both places this expansion here. So I have 1 over 4 pi integral over all of space. Well, actually it suffices if I integrate over the kr, because outside of this I have no sources, right? Outside the t mu nu is non-zero, so that's integral over a sphere. Then I have 2 kappa t mu nu, and what's the argument? The argument is t minus r over c, and then plus the correcting terms. Okay? And the second argument, sorry, is the r prime. And here again, I make this expansion 1 plus O of r prime over r and dv prime. When I say I make the far field approximation, then I mean I drop these terms. Yeah, I neglect them. That's what one calls the far field. So the far field approximation means drop these terms. And then I get the formula with which we will work in the future. So this r has nothing to do with the integration. Yeah, the r is not the integration variable. The integration variable are the primed coordinates, so I can write the r outside of the integral. And of course 2 kappa is also a constant, so I could also take this out of the integral. And then I have t mu nu at time t minus rc, and r prime, no, nothing here, dv prime, that's it already. Did I get all the factors right? Let me see. Kappa over 2 pi r, yes, that's right. Good. And now we want to see what is the leading order term? What's the leading order term which gives a non-trivial gamma in the far field? So I will now make a multipole expansion for this source term. Again, that's something which hopefully you know from electrodynamics, right? So that's precisely the same thing you do in electrodynamics. Well, there are two different things. In electrodynamics, I'm sure everyone knows the multipole expansion for time-independent fields, in electrostatic. Here, of course, I'm referring to the time-dependent situation. So multipole expansion for time-dependent fields. So that's something which you do maybe in connection with the Larmor formula when you speak about electromagnetic radiation produced by moving charges. So I define now the multipole moments in precisely the same way as they are defined in electrodynamics, just where in electrodynamics I have the charge density, now I write the energy density. That's the only difference. Yeah? And the energy density, of course, is T naught naught. So I do it without factors, okay. So I define things which depend on T. Yeah? So the monopole term I denote by capital M. So in electrodynamics, it would be the charge. Yeah? This would be the charge. It would be the integral over the charge density. So the integral goes over the region where the density is different from 0. And I do not write the charge density now. I write the energy density. And that's T naught naught of this distribution, but at the time t. Yeah, you have to be careful, not at the retarded time, of course. If I want to know what is the total energy in this domain at time t, I have to write here the same t. So when we use this expression later, we have to be careful with the retardation, and this goes over. This be integrated over a spatial variable. So that's the energy density integrated over a volume. So that's what one would call the monopole moment. Yeah, let me write it with a small m. The dipole moment is the one where I have my integration variable once here. So do I call it d? D, I think. Yes, dk. It has an index, a spatial index k. And it is the density, in our case, the energy density at t and r prime. By the way, I could write r, yeah, because in this case I don't have an r on the other side. So just as you like. So you could drop the prime here. There's no need to introduce a prime here. And then I have xk dv. So that's the way in which the dipole moment is defined. And then comes the quadrupole term, which is again the same thing, now with two indices, xk and xl dv. Well, strictly speaking, one should subtract the trace of this. That's what one, strictly speaking, calls the quadrupole moment. But this object itself contains the same information. Yeah. So it's quite common to call this quadrupole moment. But you have to be a little bit careful because some authors use the same symbol, the same letter Q for the thing with the trace removed. So the whole set of all multipole moments contains the same information if you write it in this way as in comparison to with all the trace terms removed. So because from the calculation I'm planning to do here, this trace term is just makes the the writing of the formula is more complicated, I work with this here. So I consider this as a definition for the quadrupole moment. It's not precisely what is usually called the quadrupole moment in the literature, but the set of moments contains the same information. And then comes the higher order moments. Yeah, you could also do the same thing with 3 indices. Then you would call this the octupole moment, and so on. So it goes with 2 to the power something. Yeah, the powers of 2, so it got dipole, that's 2. Quadrupole is 4. The next one is 8. 2 to the power 3, and then 2 to the power 4. What is this? 64. Something like that, right? I don't know how one calls this in Greek. What sort of moment this is. Okay, so these are the expressions which can be introduced for our source. And now we want to express our gamma, our field, our gravitational field in the approximation we are doing. We want to express it in terms of these moments. And we want to see which of the moments gives the leading order term. Yeah, in the far field, which gives the first term, which gives the contribution for an observer far away from the source. Let me see, should I do the calculation? Should I do this tomorrow? Oh, okay, I could do this here. Yeah. So the goal, let me write it here. Goal, relate gamma mu nu, our field. We want to know it at time t and at a position r to the quadrupole moments. Nonsense, to the multipole moments. Actually, it will be the quadrupole moment which gives the most interesting term. So that's our goal. So what we define here are the multipole moments. Okay. And when we do this, we will make use of the following fact. We will make use of the fact that d mu, note that d mu t mu nu is 0. Why is this true? Well, from the field equation, we get that this is 1 over 2 kappa wave operator gamma mu nu, right? And now the wave operator involves the eta, which is constant, so it doesn't matter if it is under the differential or under the differentiation or in front of the differentiation. And it involves partial derivatives, which commute with this partial derivative. So taking this together, the box operator commutes with this derivative. Yeah? So I can write, this is 1 over 2 kappa is of course a constant. I can write the box operator and then d mu gamma mu nu. Yeah? I've just used the fact that partial derivatives commute. But this here was, according to our Hilbert gauge, equal to 0. Yeah? So the whole thing is 0. So that's quite interesting. In this approximation formalism, we have the precise special relativistic conservation law. Yeah, this is energy conservation in special relativity. We have precisely this formula for the source of our field equation. Of course, this equation does not hold in general relativity. Yeah? Remember, in general relativity, the field equation implies that this holds with a covariant derivative, which is quite a different equation. But here in this approximation, it holds with a partial derivative. And we will use this. Yeah, okay, I have only 5 minutes, and the calculation is cannot be done in 5 minutes. So what we will do now, we will calculate the time derivatives of the quadrupole moments. So we will calculate, and I will do this tomorrow, calculate d by dt of qkl and the second derivative of qkl. And we will see that this here gives up to a certain factor, gives us precisely the gamma at a certain position, the field. So the far field, which is given by this integral down there, the far field is proportional to this second derivative. That's what we want to derive tomorrow. Okay, I think this is just 1 page here, so I think I can do this tomorrow in half an hour or so. And then there will be 1 hour left. And one of you asked me if I could use the last hour maybe for telling you something about the sort of research I'm doing myself. and I'm happily do this. So I plan to use the last hour tomorrow to talk on gravitational lensing, which is my favorite subject. I guess I will use a computer for this tomorrow because I have a lot of pictures for this. So we have to see how we do this tomorrow. But in any case, so we will finish this gravitational wave business in half an hour or so, and then I will speak a little bit on gravitational lensing. So see you tomorrow for the last round.